Hi everyone. In today's lecture, we will build upon the concepts that we had defined for observability and constructability, and we will try to derive conditions to verify observability and constructability. So much of the techniques that we will use, or much of the basics or the foundational tools that we will use will be similar to that we used to derive methods to identify or verify controllability or even reachability. So some of the things may not be surprising, that the concept of the concept of observability and constructability coincide for LTI systems, whereas for discrete time, so they coincide for continuous time LTI systems, whereas for discrete time systems they may not actually coincide. So there are some conditions that need to be verified. Very similar to what happened while we were doing the controllability analysis for continuous time LTI and discrete time LTI systems. Okay, so we start with again the definitions of the Gramians. So I start with a general LTV system. Of course, we will start with the continuous time formulation. So given two times T1 and T0, the observability and the constructability Gramian are defined in the following way, right? So they depend on the state transition matrix and the observability or the output matrix C, right? This one here. Similarly, for the constructability, again, so again it just depends on the way they are defined with respect to T0 and with respect to T1. Okay, so the first result. So given this definition of the Gramians, so given two times, the unobservable space is just the kernel of the Gramian defined over here, the observability Gramian. Similarly, the unconstructible space is just the kernel of the constructability Gramian defined here. Okay, we'll quickly run through the proof of this. So before that, let's quickly recall how the unobservable subspace was defined. So the unobservable subspace was C of T phi T T0 X0 equal to 0 for all T in T0 and T1. Okay, and then the system was observable if U T0 T1 is 0. Okay, so what we want to prove now is, or show now, is a relation between the unobservable space and the observability Gramian. Okay, so the proofs are pretty straightforward. So we just show one proof, and then the other one will be quite obvious. T0 T1 is the kernel of WO T0 T1. Okay, so from the definition of the observability Gramian, so for every X0 in Rn, we have X0 transpose WO T0 T1 X0. So this is I just plug in the definition of observability Gramian. So I have a X0 transpose phi tau T0 with a transpose C tau with a transpose C tau phi X0 and d tau. Okay, so this is simply T0 to T1. You can write it as the following: C tau phi tau T0 X0 square d tau. And therefore, x naught belonging to the kernel of the observable space would mean that, so x naught belonging to the kernel would mean the left hand side would be 0, and therefore, the relation in the integral also will go to 0, which means C tau phi there will be tau t naught x 0 equal to 0 for all tau within t naught and t 1. Okay. Now, look at this. So, this x 0 when it belongs to the kernel of W, from these two steps it also means that this x 0 satisfies this relation. And now, we go back here, whenever x 0 satisfies this relation, this means that this x 0 belongs to this. Okay. So, what is this x naught? So, sorry, what is this this subspace? This subspace is the unobservable subspace. Okay. So, that concludes the first part. So, whenever x naught is in the kernel of W 0 or W O or the observable Gramian, it also belongs to the unobservable subspace. Okay. Now, the second part of the proof. Conversely, we start with assuming that let x naught belong to the unobservable subspace. So, if x naught belongs to the unobservable subspace, this also means that C tau phi t naught x naught is 0, okay, sorry, tau here, for all tau in t 0 t 1. Okay. So, now look at the definition of the Gramian, which was here, and say, okay, I just pre and post multiply this W naught by x naught. So, x naught transpose here and x naught here, that would mean that, okay, so this would imply that x naught would also belong to the kernel of W naught t 0 t 1. So, I am just using this fact, right. So, I multiply x transpose with W times x. So, with a, so this will be equal to 0, implies that W naught of x 0 is 0, and essentially this would mean this one. Okay. So, why is this true? This is true because so this kind of equality relating to this one is true if and only if this W is a positive semi-definite matrix, which is true in our case, right. Okay. So, that concludes the proof, and then on very similar lines you can prove the second relation, that the constructible space is the kernel of WCN. Now, what is the definition of observability then, right? So, we just recall the definition that we had for observability, and it said that the system is observable if its unobservable subspace contains only the 0 vector, right, or in other words this set is simply 0. Okay. Now, so how do we check the or how do we now develop the or derive the rank conditions for this? So, the first statement, which is a direct consequence of what we said here in the previous slide, is that the system 1 or the LTV continuous time system is observable if and only if the rank of the unobservable subspace is equal to n. Okay, why is this true? So, we are so what we said is that the unobservable space is also equal to the kernel of W naught. So, this is the observability Gramian. Okay. Now, so this should only contain the 0 vector, okay, which means W0 times T0 T1, if x0 is in the kernel of it, this should be valid only when x0 equal to 0, for which it means that this W naught should be invertible, right. So, this x naught, whenever this relation is satisfied, this means that this x naught is in the kernel of this observable Gramian. Now, this kernel is equal to the unobservable subspace, and for observability this unobservable subspace should only contain the 0 vector, okay, which means this x naught should be the 0 vector. So, this is a 0 vector if and only if this W is invertible or it is non-singular. So, in other words, this also means that invertibility of this W naught means that it is observable if and only if the rank of W naught T0 T1 is equal to n. Similarly, with the constructible system, or to check constructibility of the system is only if and only if the rank of the constructibility Gramian is equal to n. Okay, little example, nothing really special here. I am just computing the Gramian. So, and we just recall some tools what we learned earlier, right. So, I have x dot equal to ax, y equal to ct. So, in most cases I would not really need information on the input, right. So, whenever most texts, when they talk of observability, they kind of neglect the input in the computations. That's for obvious reasons, because what I am really interested in, how do I measure the state or x0 from the output equation, right. So, the input becomes a little redundant, because all those quantities can be computed and just can be added later on. So, so we just ignore the input and then just deal with systems like this, and all the results which are valid here are valid for the systems with input. Okay. So, my AT is of this form, C is of this form. I can easily compute the state transition matrix. We had several methods learned in week 4 of these lectures. So, from this phi, the state transition matrix, I can compute the Gramian. So, once I have the Gramian, I can compute the rank, and the simple computations show that the rank is 1, whereas the full rank is 2, and therefore, the system is not observable. And I can actually construct the observable subspace as the kernel of this one, which just is any vector alpha comma 0 will be in the observable subspace of the system. So, therefore, the system is not observable. Okay. So, the next thing we will see shortly is how to, given the Gramian, how do you reconstruct the state. So, it turns out, okay, we will do the computations and then come back to this result here, that okay, I start with x dot is AT xt plus bt ut, and y is c x plus d u. Okay. So, so we had this these computations the other day, right. So, we had this y tilde and so on. So, we had this y tilde defined as c of t phi t naught x naught, for all t in t0 t1 with y tilde was equal to y of t minus t naught to t c t phi t comma tau b tau u tau d tau. So, this we just refer to lecture 1 of this week on how we get this derivation, and then okay, you have a minus dt ut also here. Okay, now take this expression here, and what I do is we free multiply this by phi with the transpose and C transpose, integrate this from T naught to T1 with, right, I take this equation, I pre multiply this with phi transpose, C transpose, integrate this from T naught to T1, and what I get on the right hand side is T naught to T1, again I pre multiply this by phi transpose CT transpose C phi okay. So, so this entire term here in the integral without the x0 is just W O T W O T naught T1 times x0, right. This is my observability Gramian, this entire term here with the integral without this x naught. So, this is what we have, and on the left hand side I still have T naught to T1 phi T naught transpose C T transpose y tilde dt. Therefore, now given this I can compute x naught as okay. Again I can compute x naught if and only if this this W is invertible, right. So whenever the system is observable, which means this W naught is invertible, I can reconstruct the state from the Gramian, right, from this and this. Okay. So now just the result just says the following, right. So suppose we are given 2 times T naught and T1 and an input output pair U T Y T. So whenever the system is observable, I can reconstruct x T naught with this inverse of the Gramian and with this phi C and y tilde, where y tilde is just this expression, right. So again we use make use of the fact that whenever the system is observable, this W should be invertible. Okay, and similarly I can do it for the constructible to check for constructibility, right. So I'll skip the steps. These are exactly similar to what we do in the observable system. Okay, a nice interesting thing before we go into the proofs of say like the eigenvector test or the PBS test or the Lyapunov test for observability would be to just check if there is some kind of a duality between controllability and observability, right. So we defined Gramians there, we defined Gramians also here, we had something to do with the subspaces over there, the reachable subspace, the unobservable subspace here and so on, right. So we will see if we can make a nice connection between what we derived in week 7 and what we are about to derive now. Okay, so let me say I start with a system, okay, continuous time LTI system, x dot is Ax plus Bu, y is Cx plus Du. Okay, so whenever the system is controllable, it means that the rank of the controllability Gramian is n, where the controllability Gramian is just given by this integral over here. Similarly, this system 2, so this guy is observable if and only if the rank of the observability Gramian is equal to n, which means something like this holds true, right. So which means the this should be invertible and the Gramian looks something like this. Okay. Now, let me define alternatively a system in say some other coordinates x tilde with x tilde dot as A transpose x tilde plus C transpose some u, y being B prime, or so sorry, these are all transposes, right. A transpose, this is C transpose. Okay. So, alternatively we will use sometimes we use this notation, sometimes we use transpose. So, both of them actually mean the transpose. Okay, sorry about those confusion of notations, but essentially this this prime also would mean transpose. So, x tilde is A transpose C transpose, y tilde is B transpose x tilde plus D transpose U tilde here. Okay. So, controllability of this system would again mean that the rank of WC equal to n, where the controllability Gramian takes now this expression. Okay, and then this rank should be equal to n. Similarly, this system 3 is observable whenever the rank of this observability Gramian given by this expression is equal to n. Okay, now look at this expression here, the way the controllability Gramian is defined here and the way the observability Gramian is defined here. Well, they look the same, right. So, the WO here is equal to WC tilde. Similarly, look at how the observability Gramian is defined here. The observability Gramian here looks exactly similar to the controllability Gramian here. Okay, so there is something nice here, right? Something that we can conclude saying that if we are given again 2 times T1 T naught greater than or equal to 0, this system 2, okay, x dot is Ax plus Bu, is controllable if and only if the system 3 is observable again on T naught T1, right, this one. So, this is the system 3. So, the controllability condition over here was equal to the observability condition in the previous slide, and similarly the controllability condition over there was equal to the observability condition here. So, I can just write down the steps here. So, I can just conclude that controllability of 2 is equal to the observability of 3. Similarly, if 2 is observable, then 1 is also controllable, and it is with both ways, right. So, 2 is observable if and only if 1 is controllable, right. Similarly, I can do it for the reachable and the constructible Gramians, right. So, so system 2 is reachable if and only if the system 3 is constructible, and vice versa, that system 2 is constructible if and only if the system 3 is reachable. You can again check by writing down explicitly the Gramians, right. Okay. So, again some little observations. So, the notions of observability and constructibility do not depend on the time interval considered. Like for example, it is not really necessary to specify the time T naught T1 under construction, which essentially means that if I can uniquely reconstruct the state x naught at T naught, right, considering the interval T naught and T1 for which I know the inputs and the outputs, then it is also possible that I can construct x naught at some T naught tilde given any other interval T naught tilde to T1 tilde, right. So, it is, so when I say it does not really depend on time interval considered, it means this one, right. So, if I can reconstruct the state in this interval, I can also do it in this interval. So, I can find out x, if I can find x T naught, I can, it is also equal to saying that I can actually find x T naught tilde also. Okay. So, the notions of observability and constructibility coincide for continuous time LTI systems. So, which means that if one can reconstruct the state, so if one can reconstruct the states from future input and output, one can also reconstruct it from the past inputs and outputs. Okay, it's a similar argument of saying that the notion of reachability and controllability were similar in the continuous time LTI systems. Okay, so a little caveat here, because a lot of things we did here just by looking at the transpose, right. So x tilde dot was A transpose, and then in the Gramian I just replace A by A transpose, and everything works beautifully. Whereas a little care must be taken while I am dealing with LTV systems, in the sense that for LTV systems the state transition matrix must be the transpose of this, the state transition matrix of the dual system must be the state transition matrix of the original system. So, simply replacing A by A transpose will not work. So, this is a little care we may need to take while we are dealing with duality for LTV systems. Okay, so that concludes this lecture, where we saw Gramian based conditions for defining unobservable subspace, or even under what condition is the system observable and under what conditions is it controllable. In the next lecture, we will quickly run through the concepts of observability for discrete time systems, and also do some very basic observability tests. Thanks.